Hi, this is Edwin Tembo. Today I'm going to be discussing ChemicalX, a deep learning package for drug pair scoring. So this package was created by a team from AstraZeneca, Harvard Medical School, and Vanderbilt University. And their goal was to create a way to help drug safety researchers, machine learning researchers, and other drug-related professions to find a better way to determine how drugs interact under certain contexts. So the problem is that as it is now, most of the drug pair scoring occurs in labs. It has to be physically done to get an outcome. So the goal with ChemicalX is to find a way to reduce that to, probably maybe mere minutes or hours with a deep learning model. If the deep learning model is good enough to classify the interactions between drugs, then this can become a much faster process, potentially saving lives, and making the world a better place. So, what is drug pair scoring? This is a process of actually finding the outcome when two or more drugs interact under a certain context. The context in this would be as a biological life form, perhaps a virus, or it could be another chemical such as a drug. There are three main categories, which is drug-drug interaction, polypharmacy, and drug synergy. I won't get too deep into the definitions of those. There's plenty of information online regarding what they consist of. And then now off to the model itself. It is basically an encoder which takes in an input for each drug, which is a feature set and its labels, and encodes it into the feature's latent space. And so once that latent space representation is available, it is passed on to a head layer which outputs a probability to classify the interaction between the two drugs. I guess to get the score between the two drugs. And the probability is measuring one of these three items, including polypharmacy, interaction, and synergy. So for polypharmacy, it's trying to determine the probability of polypharmacy side effect Z, and for interaction, the probability of interaction Z, given the two drugs, and for synergy, the synergy at treating disease Z when the two drugs are administered together. The requirements for this are Python 3 plus PyTorch, PyTorch Geometric, and Torch Drug. This will take about 30 minutes or so to install on, say, a Google Colab machine. So it takes a little bit of time, but once it's up and running, it's fairly straightforward. The package itself comes with some pre-processed data sets. Basically, all a user needs to do is select the appropriate data set for the appropriate task, and also select the appropriate model. Once that's done, it's a fairly straightforward process. However, I will say that the data is somewhat outdated. I believe the last time it shows an update was sometime in 2022. So if a user would like to get more recent information, they would have to update the data themselves. And the Jupyter notebook provided will show how someone might do that. Okay, this is just a listing of the pre-processed data structures available. I won't get too deep into those as well, but as we all have seen, this includes the SMILES representation of each molecule, and then the context can be a biological or a chemical compound. Then the labeled triple is the basically the identifiers for the two drugs and the label itself. So a 1 or 0, whether this, for example, if it was a drug-drug interaction, it would the label would be a 1 or 0, indicating a binary relationship of whether the interaction would occur under a certain context. For the models themselves, there are several models provided for each specific domain. As you can see, there are plenty of options. Some of them may need a little work, but for the most part, it seems fairly straightforward. And as you can see, the encoders are either feed-forward networks or graph attention networks or graph convolutional networks. And the good part is that you can actually get to the GitHub repository and, if needed, update the code to make it work for the situation that's required. A few abstractions are provided as well. That's an easy data loader, batch generator, and a model pipeline for training and inference. It's your typical abstractions you see with with data loaders and batch generators. It's just a fairly straightforward way to get the data loaded and get the model trained. Okay, and here's some sample code. As you can see, it's very simple as well. You simply import the library for the data set and the batch generator in this case, and the loader actually makes it very simple for you to put in what's required for the batch generator here. And once that's done, all you would have to do is get the generator to generate your batches in a training loop, and we'll see how that works. Okay, and here's also a sample code using just a regular training loop. So that batch generator could be used in this way. Just a simple. This is just for one loop. It's just code to show how one loop might be formatted. Again, it's your typical PyTorch training loop. Nothing special. You would have to, of course, select the hyperparameters and maybe put this inside an actual training loop. And again, the Jupyter notebook provided will show how someone might do that. Okay, and now here's a sample code showing the pipeline. In this case, again, it's very straightforward. There's no loading data with a data loader. All you do is import a data set and supply it as a parameter to the pipeline function, and that's all that's required. Or is this a yes, to the pipeline function, and that's all that's required. Once you do that, all you have to do is run the function, and depending on the epochs, it takes a little bit of time to come up with the results, and you can print out the results or save them somewhere. Again, this is very easy, but it's also not very flexible. So in some situations, it might be more suitable to use the regular training loop with the batch generator. And some sample code for inference here. Again, something very straightforward. All you have to do is import a few libraries, supply your data, and it's a very, very simple output of your predictions. Okay, thank you very much. That's all I have today.